Tokyo's Aqualine was built to move traffic straight under Tokyo Bay. Today, because that tunnel cannot simply be widened, the road has to watch traffic, slow it, warn it, and manage it before congestion turns into a safety problem. That reversal is the whole story. The surprising part is that it did not happen because the project failed. It happened when the crossing finally became easier to use, demand surged into a tunnel with fixed space, and Tokyo ran out of simple physical ways to add capacity. Before the Aqualine, crossing between the Kawasaki side of Tokyo Bay and Kisarazu on the Chiba side meant going the long way around. The problem was not the destination. It was the bay itself. A direct line across the water could cut out a huge detour, which is why this route was worth attempting in the first place. But the moment engineers chose the shortest path, they also chose the hardest kind of highway to live with later. There was no continuous land across the bay. No easy corridor to widen. No spare strip beside it waiting for extra lanes. To make the shortcut real, the road had to split into two different structures, a long undersea tunnel on one side and a bridge on the other. That design solved the original geographic bottleneck brilliantly. It also locked a large part of the route inside a fixed, enclosed tube. And that matters because everything that happens later flows from this one decision. The Aqualine works because it takes the straight path. But the straight path forced Tokyo to build a highway with much less room to adapt once demand changed. A surface highway can often be widened one shoulder at a time. The Aqualine could not be treated that way. Its tunnel was bored through the seabed using large shield machines. As the machines advanced, workers installed precast lining segments behind them. Ring by ring, the passage became a sealed structural tube. That method made the crossing possible. It also made the tunnel's geometry permanent. The lanes, clearance, walls, emergency walkways, ventilation spaces, and services all had to fit inside one carefully calculated bore. The construction began in 1989. The route opened on December 18, 1997. Between those dates, engineers were not simply building a road. They were manufacturing an environment beneath the bay. At its deepest point, the tunnel reaches roughly 60 meters below sea level, depending on how the measurement is defined. That distinction matters. A tunnel can be described by its depth below the water's surface or by its position below the seabed. Either way, modification is not comparable to adding a lane beside an ordinary road. A second bore could theoretically be considered. But it would mean another major undersea construction project, new approaches, new safety systems, and enormous cost. The existing tunnel cannot simply be opened up from the inside. Its lining is part of the structure. Its systems are part of the safety envelope. The builders were not just digging a passage under the bay. They were fixing its shape for decades to come. In the middle of the bay, the Aqualine does something unusual. It surfaces. Umi Hotaru is the point where the undersea tunnel hands traffic over to the bridge, and that makes it far more important than a scenic stop in the water. It is one of the route's key operating nodes, a place where the tunnel environment changes, where drivers change pace, and where the entire crossing stops behaving like a simple, uninterrupted line. That is why Umi Hotaru matters in this story. A fixed tunnel is already restrictive. A fixed tunnel that feeds into one concentrated transition point is even more sensitive to disruption. Vehicles emerge from an enclosed bore. Some continue straight through. Some slow as the road opens up. Some are influenced by the service area environment and the change in road character around the island. So even before the later traffic story begins, the Aqualine already has a built-in pressure point. Not necessarily because Umi Hotaru causes every cue, but because it gathers several different behaviors into one tightly managed part of the system. That gives the crossing something memorable and useful at the same time. It is the hinge between tunnel and bridge. And later, when the road becomes busier, hinges are exactly where stress starts to show. The Aqualine's central traffic problem did not begin when nobody used it. It began when more people finally did. In its early years, the route struggled with underuse. For a project this large, that was a serious problem. A direct crossing under Tokyo Bay had been built, but the price of using it limited how many drivers were willing to make it part of their routine. Then, toll policy changed. The crossing became dramatically cheaper, and that changed the calculation for drivers almost immediately. More people started using the route because the route now made financial sense, not just geographic sense. This was supposed to make the project work better. And it did. But it also triggered the reversal that defines the Aqua Line today. The lower toll could increase demand. It could not increase tunnel space. It could not add easy new lanes inside the Undersea section. And it could not remove the friction created when a fixed tunnel, a major transition point, and heavier traffic all met inside one system. That is the moment the story turns. The Aqua Line had already solved Tokyo Bay as a map problem. Now it had to deal with success as an operating problem. Because once traffic rises inside a route that cannot easily grow, every slowdown matters more. Every queue forms faster, and every disruption becomes harder to absorb. What had once looked like a straightforward shortcut now needed something more than concrete and steel. It needed active control. On an open highway, congestion is frustrating. Inside a long enclosed tunnel, congestion is also dangerous. That is the difference the Aqua Line has to live with. If speeds suddenly collapse in open air, drivers may still have more sight distance, more room to react, and more ways for the disruption to spread out. Inside a tunnel, walls confine the problem. A stopped vehicle, a minor collision, debris in a lane, or even a sharp speed difference can push traffic backward through the bore much faster than the road can recover. And once vehicles begin stacking up underground, the stakes change. Now visibility matters more. Access matters more. Smoke would matter more. The time available to detect trouble and react to it matters more. That is why the Aqua Line cannot treat congestion as a simple convenience issue. In a fixed tunnel, flow management is part of safety management. From the driver's seat, the road can feel simple. Lanes, lights, walls, darkness ahead. From the operator's side, it is something else entirely. It is a monitored environment where a speed drop can signal the start of a queue, where a camera check can confirm whether the issue is ordinary traffic or a stopped vehicle, and where upstream warnings matter because drivers behind the problem may not see it until it is too late. That is the key shift in the whole video. When the road cannot create more space, it has to create more time. More warning. More order. More control before a slowdown turns into a chain reaction. The Aqua Line's control system follows a simple loop. Detect. Interpret. Intervene. Traffic detectors track changing flow. CCTV gives operators visual confirmation of what the numbers mean. A sudden reduction in speed may signal ordinary congestion. It may also point to a breakdown, a collision, debris, or a vehicle stopped where it should not be. The system cannot treat every anomaly as the same event. That is why cameras and human operators remain important. Once the condition is understood, the road can communicate with drivers. Variable message signs can warn of queues or restrictions. In-tunnel speed displays can reduce the speed difference between vehicles approaching a problem. That does not create another lane. It prevents available space from being consumed by abrupt braking and unstable flow. If an incident blocks movement, operating procedures can restrict lanes and coordinate emergency response. Ventilation systems manage air quality during normal traffic and become critical when smoke or fire changes the tunnel environment. Emergency walkways and refuge provisions give people a route away from moving traffic when leaving by car is no longer realistic. The system also watches the asset itself. In a country exposed to earthquakes, monitoring for movement, settlement, water ingress, and structural change is as important as watching vehicles. The highway is being observed from several directions at once. traffic conditions, driver behavior, air quality, structural condition. That is the control layer the title points toward. Not a single artificial intelligence deciding where everyone drives. A coordinated operating system that turns information into action. The Aqualine is not being made larger. It is being made more responsive. That principle appears across enclosed megatunnels around the world, including systems such as the Channel Tunnel, where central monitoring, communications, and incident procedures are essential because the physical environment is difficult to alter. The technology is not replacing the tunnel. It is compensating for the tunnel's permanence. Tokyo built a route through a space that could not easily expand. So the road now manages success through data, warnings, speed control, ventilation, and response. The original highway was designed to move traffic. The modern Aqualine has to do something harder. It has to keep traffic moving without allowing movement itself to become the danger. A road built to overcome geography now depends on intelligence it carries through every kilometer.